All right, hello guys. Welcome to my second video. I'll be talking about how do neural networks learn in this video. And before getting started, my name is Adrian Flores. It is actually February 4th of 2025, and this video is specifically made for my Computer Science 4540 class, also known as Intelligent Agents in Learning Environments. Before getting started, I kind of want to do a recap to talk about what I talked about in my previous video, because it does correspond to this current video, talking about talking about a little bit more in detail about neural networks. So what I talked about in my previous video is how neural networks are actually very good at classifying handwritten digits. And when it comes to classifying handwritten digits, it is actually used in a grid, in a 20 by 28 grid. And each pixel corresponds to a grayscale value, which is between 0 and 1. But when I talk about the pixels, I kind of mean about neurons, which is these little circles that you see on the image. So each neuron is actually going to correspond to 0 and 1. And depending what the value is, it actually depends how bright it will be, right? So if the value is like 0.9, 0.8, the circle would actually be really white or really bright. But if it's super low, like 0.2, it'll pretty much just be black or gray. And when doing the input layer, it has a total of 784 neurons. And another thing to remember is that the activation of each neuron is based on the total weight sum, the weighted sum of the previous layer, plus the bias. So as you can see, this is the first layer, but the second layer for the one neuron, it actually corresponds to the weighted sum of all the neurons. So depending on what the weight is, it'll create the value for the next neuron and the next value. And that's something very important to learn. And the values do vary depending on how bright the neuron is. So I'll be getting a little bit more in detail about the actual topic, which is talking about how do neural networks learn. And the first step, most importantly, is being able to train the data. In this example, the data is actually full of thousands of handwritten digits. So in this example, the network that we have right now, it's currently being trained with the thousands of handwritten digits and with their corresponding labels. And but what I mean by this is in this image, you can see the handwritten number one, and the corresponding label it would have would be the actual one. This pretty much means that the image right here that you have would be one, right? And it corresponds to every other image there is in the data set. And the total weighted sums and biases that is used throughout the whole network is about 13,000 weights and biases, which is a very big number due to how big the network is actually is. And once the training data is actually being done, it's then given more data on top of that. But compared to this data is actually, I guess you could say never before seen data. So you would give it new handwritten digits to be able to determine the accuracy of the network that you have right now. So you would pretty much give it new data on top of the data that's already been trained onto it to be able to determine the accuracy of it. And this is when we get into the topic of cost function. It gets a little bit more easier along the way, but you could kind of think of it of similar to calculus due to the equations and the vectors that it has. So, like I said before, each neuron is pretty much connected to all the neurons in the previous layer, and each neuron actually has a different value for the weight. So the weighted sum defines the activation of each neuron. So like I said before, depending what the value is, it'll pretty much determine how bright the neuron would be or what the grayscale value would be for that current neuron. So let's say, for example, in this network that we have, we pretty much assign it random weights, random biases, everything random, right? Let's say we give it everything random and we give it a assigned handwritten digit, and we want the network to identify what the final output would be. And in reality, when doing so, the accuracy might not be 100% or it might not even be close to 100%. But this is what we're um, trying to use just to show an example of how cost function can make a difference. So when doing everything randomized, let's say for example we give it the number three, right, to want to identify it. In reality, it'll come out to something like this, which is pretty much just trash values. Like it says right here, utter trash. This is what we don't want. So you can see that it lights up 7, lights up 8, lights up 3, and pretty much every other number besides 5, right? But this is not what we want as our output. We want our output to just be a single number, which is number 3, and for the neuron to be lit up with the highest value, or just in general, the only number to be lit up for the final output. And this is when the cost function actually comes into play. So the cost function pretty much what it does, it adds up the squares of the differences of each incorrect calculation and the value you want them to have. So in this example, uh, like I said before, we want to give it the handwritten number 3, right? So this will correspond to 0, 1, 2, 3, right? So we will subtract the value to 1 because we want the correct output to be 3, which is this one. And then we will subtract the differences of each incorrect calculation to every other number, right? So it would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then once we do so and add up all the squares and the final results of it, you will get something like this, right? So once you actually do the summation of all of them, you would either have a small number, which would be 0.03 in this example, or have a big number, which would be 3.37 in this example. And this number is actually very important to remember and to be able to notice how big or small the number is, because if the number is small, that just means the network is very confident in being able to identify the right output, which which is 3 in this example. But if the number is very big in this example, that just means the network is very uncertain, which is what we don't want. That is the absolute worst in this current situation. And the easier way to find uh, our result could pretty much be able to find the average cost. But in this example, there's actually thousands and thousands of training examples, which is what we'll have to find the average cost of. But if we do find the average cost, and when we do find the average cost, it is pretty much the measure of how lousy the network is performing. So as you can see right here, the cost function, it takes the total input of 13,000 weights and biases as the input. And for the parameter, um, it is the thousands of training examples. And for the output, it is the one number, which would be the cost. Compared to the neural network, where it takes a lot less input numbers or pixels, but the parameters would be 13,000, which is when it starts switching to the cost function. So to make it much simpler, we could just create a simple function that has one input and one output instead of using all 13,000 possible weights. So when doing so, it'll actually create a graph like similar to this. And to do so, the importance of this is to be able to find the local minimum, right? So to do so, we would actually have to determine whether the random point that is being given on the graph, whether we have to move it to the left or right. So to do so, we could just find the slope of each side and determine which one has the lowest uh, size, right? So if it has the lowest, in this example, to keep going down and down until it reaches the bottom. But of course, there is a smaller minimum here, but that would be for the global minimum, which is a lot more complicated. But in this situation, we're looking for the local minimum. So you could kind of think of it as a ball rolling down from the graph and determining where it would actually land. And in this example, it would be over here. So this is when gradient descent actually comes into play, which is this picture on the left. And this is very important because it's able to find the direction to change weights and biases in order to be able to decrease the cost function. But the gradient also gives the direction of the steepest ascent of the cost function, and it indicates how steep the slope is. So this is what's been happening in the picture. It keeps going down and down until it reaches the most steepest slope, which is over here, as you can see right here in the little line. And to do so, it'll just keep repeating itself, computing the same gradient descent in small steps, and then just repeat, 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 repeat until it finds the steepest slope. And then once we have the values from the negative gradient, it would actually show which weights and biases have the most impact on the cost function. So they could be either negative or positive, as you can see right here, 2.4043, negative 1.12. That is what we're looking for. And what I mean by what we're looking for is because it actually shows which changes would actually have a bigger impact or smaller impact. So as like I said before, the bigger numbers would actually have a bigger impact compared to the small numbers. So as you can see right here, 0.78 would actually increase a lot, which in other words would actually have a bigger impact than compared to negative 1.25, right? Which is what has a negative impact. So what they noticed was actually that when studying neural networks, they realized that sometimes it tends to memorize data rather than learn the data. So in this example, they give a neural network randomized labels, right? So in reality, this would be a real fork, but in the randomized data, they give it the label trilobite, or the line would be considered cow. And when doing so, they noticed that the training set is actually very 100% accurate compared to the actual valid data set, which is what they were very surprised of because that's when it kind of gave the hint that they tend to memorize data rather than learn it. But as you can see, the testing set, it's a lot more smaller and smaller, depending how randomized the data actually is. So with the validated data, it has a lot higher accuracy. But when it gets more random, it has well like 10% right here, which is what we don't want. And another topic that we talked about was uh DeepMind's impact on science. So DeepMind is pretty much um kind of like an AI company, but the CEO is Demis Hassabis. He is from London and he actually won the Nobel Prize for being able to solve the 50-year-old problem, which is predicting complex structures. His inspiration was actually the game called Go, which was the early work of DeepMind because it gave him kind of like a good understanding of how AI would work in the early steps due to the many different data that could be acquired from these video games. And along the way, they created a neural network that would actually help the AI determine what's the best situation, best step to be done in a current situation, which is why the neural network was being made for this situation. But in future years, it was actually used to impact IRL problems in science. And the impact or the problem they actually went with was actually being able to figure out the protein folding problem, which is actually what they pretty much accomplished and why they won the Nobel Prize, due to the fact that they were able to predict the protein's 3D structure from its 1D amino acid. So in this example, the sample sequence would be all these integers or all these letters in this example, and what they got. This is not the right picture, but in reality, they would get an image, 3D image similar to this one. And the impact of their company was that they made it open source, allowing millions of researchers to use in different areas such as fighting plastic pollution or tackling antibiotic resistance. And that is pretty much my understanding of this week's videos and assignments. And thank you guys.